Good evening, everyone. I'm Lisa Hoover coming to you live from Chabot Space and Science Center. And welcome to our Supercomputers and Super Lasers Livermore's Big Science Talk with Dr. Leland Ellison from Lawrence Livermore National Laboratory. We're so excited to be coming to you live virtually on Facebook Live tonight. During our closure, we've been busy behind the scenes developing new programs and new ways to engage with all of our audiences, and we're looking forward to sharing new activities, videos, and programs with you real soon. Now back to tonight's program. Our special guest is Dr. Leland Ellison. He is a computational physicist at the Lawrence Livermore National Labs. He develops physics software for modeling high energy density systems. His particular areas of research include plasma physics and numerical methods for solving differential equations. Aside from his research efforts, Leland is actively involved in science outreach throughout the community. He's a regular presenter for the laboratory's Fun with Science program, where he performs science demonstrations for elementary and middle school students. And he's the star of Lawrence Livermore National Laboratory's Learning with Leland YouTube series. Stay tuned after Leland's message because we will be answering some of your questions live. So without further ado, I'm going to turn it over to our guest speaker, Dr. Leland.
Thank you so much, Lisa. Wow, it is really a pleasure to be invited to this event hosted by Chabot Space and Science Center. I'd like to extend a big thank you to Jessica Williams and Lisa Hoover for the invitation to come talk to you today, as well as all the substantial preparation that went into this event. It might only be an hour on Facebook, but I assure you many hours went in behind the scenes to make sure all the tech would work smoothly and promote the event. So thank you so much to them for all that hard work. And thank you all for tuning in this evening. I have to admit that I was reflecting today on what a special opportunity this is. I get to talk to a big crowd of people who I don't normally interact with. And I went on to further reflect that it was interesting that, of course, my opportunity to do so would come during a pandemic when I have to be stuck at home and not in person in front of all of you filling seats at the Chabot Space and Science Center, say, as well as after it's been 4 months without getting a haircut. So the good thing about science is that it's about your ideas and not your appearance. So I hope you enjoy hearing those today and can take my shaggy haircut as a statement to that effect. So as Lisa mentioned, I am Dr. Leland Ellison. Many people just call me Lee. And I'm a computational physicist at Lawrence Livermore National Lab, where I have been since 2016. I came out here to California after finishing my PhD in plasma physics at Princeton University. So the reason I'm here today is to share with you just a couple of highlights of the work that's going on at Lawrence Livermore National Lab. So Lawrence Livermore National Lab, we also call it LLNL for short, is in the town of, you guessed it, Livermore, California, just over the hills from Chabot Space and Science Center. And it is one of 17 national labs run by the Department of Energy. So there's this huge national lab complex sprawling across the entire country, and they all specialize in different things. Lawrence Livermore specializes in a lot of different things. We have our high energy density physics program, which I'll be talking to you about tonight. Of course, our supercomputers we are very proud of, and I'll also be talking about tonight. But I don't have time to talk about a load of the other things that we have going on, including quantum computing, artificial intelligence, cancer biology, neuroscience. There's just a tremendous number of things that happen there. A lot of it's really exciting, so I hope I can catch your interest to look into some of that some more. So as someone who, since a young age, was really interested by math and science, working at LLNL is truly a dream job. And aside from the great people that I get to work with that make it really interesting every day, the other fantastic thing about working there is that we have some of the biggest toys in the world. Now, of course, by toys, I mean high precision and high performance scientific instruments. Their purpose is not to entertain, but is to do science. But that wow factor and the fun of working with them truly never goes away. And it is that inspiration that I hope to share with you a bit tonight. So in particular, I'll be highlighting two of the crown jewels of Livermore's facilities. One is the National Ignition Facility, the world's most energetic laser, and the other is the Sierra Supercomputer. So in the first part of this discussion, I'll be talking about the National Ignition Facility, or NIF for short. And it has the world's most energetic laser there. We actually have 192 laser beams. It takes 3 football fields length of optical path and capacitors and amplifiers to generate this laser pulse, which we then focus onto these tiny little hydrogen pellets. And I'm going to be talking about why we're doing that and showing a video of what it looks like to deliver such incredible power on such short times and with such high precision. The other part of the talk will be about supercomputers, and that's really where I fit into the picture as a computational physicist. Now, this talk comes at a fitting time, although a challenging one for Livermore. So when I wrote the advertisement for this talk, we were home to the 2nd fastest supercomputer in the world. Now, just this week, the new top 500 HPC computing list came out. And what do you know, but Japan unveiled a new computer, which has taken the #1 spot. So that's also terrifically exciting. And I assure you that our now #3 fastest supercomputer is still really impressive, and you'll be excited to hear about it today. But if you stick around to the end, I'll be sharing with you some of the plans looking forward when Livermore is shooting to reclaim the #1 spot on the fastest supercomputer list in just a couple of years. So it's a very exciting time for supercomputing. So back to the lasers, let's begin tonight's story with the National Ignition Facility. Really a flagship experimental facility that we have at Lawrence Livermore is this National Ignition Facility. If you take 580 from the San Francisco Bay and cross over the hills, just before you head up the Altamont Pass, you can turn right onto Greenville Ave. Maybe you're headed to go wine tasting in the Livermore Wine Valley. If you look over to your right, you will see this large building. It's kind of beige, and it might look like a large office building, but there's no windows there. And it is in fact home to the most energetic laser in the world. So you'll get to see a glimpse of that facility in a video I'm going to show you in just a couple minutes. We'll kind of peel the roof off and get to see what it looks like on the inside, and some computer animations of the process of generating laser beams. But I wanted to motivate this video and give you context of why we are bothering to create 192 laser beams and deliver them on fractions of a second time scale. And the reason for that is baked into the name of the National Ignition Facility. The intent of the facility is to learn physics related to the process of ignition. So let me take a little time to explain what ignition is. So to understand ignition, you need to understand fusion. So fusion is one of 2 types of nuclear reactions, and it is the type of nuclear reaction that fuels stars, including our very own sun. And in fusion, you have 2 light atoms, maybe hydrogen, and you get them going very fast. You have to heat them up very hot. And if they get close enough together, then they'll stick together. The nuclear strong force takes over, and out comes helium and a whole bunch of energy. The other type of nuclear reaction is fission, where you take a very heavy atom, it has lots of protons and neutrons, something like uranium, and you split it apart into elements that are lighter and smaller, and that can also give off energy. So to understand why it takes such a tremendous facility, we've gone to enormous lengths to be able to study nuclear fusion. It's helpful to have a mental picture of the physical processes going on during fusion reactions. So as you probably learned in school at an early age, hydrogen nuclei are positively charged. They have a proton, so they push against each other. Like charges repel, right? So we start off with these 2 hydrogen nuclei, and I kind of think of them like tennis balls. They're little positively charged tennis balls. They want to repel each other. I like to think of them as being connected by some very stiff spring, and that spring is pushing them apart. Now, imagine that these two hydrogen tennis balls are also covered in superglue, a really, really strong superglue that as soon as it touches some other superglue, it is going to stick and stay stuck. Well, that superglue is an analogy for the nuclear strong force. So when the two hydrogen nuclei are relatively far apart, that spring, that is the electric force, is pushing them apart from each other. And it takes a tremendous amount of energy to push against that spring, that repulsive force, and get them close enough that the superglue makes contact, and then the nuclear strong force takes over. That superglue is so strong and stronger than that spring. Out pops your helium and a whole bunch of energy, right? So it's that repulsive force that requires us to have tremendously high temperatures. In the sun is very hot and it has gravity and it likes to hold all its hydrogen atoms together and its helium atoms together. And it's hot enough that they can bounce around, and every once in a while you get some fusion events happening, and that gives off the energy that powers the sun. But at the National Ignition Facility, we heat those hydrogen atoms up with our giant laser beams. Now, the notion of ignition is related to how many fusion reactions we have happening. We have for several decades been able to make some fusion reactions. We can watch these helium atoms come out. It also gives off neutrons. We can measure those. But it's been a massive challenge for the scientific community to, in a laboratory setting, release more energy with that thermonuclear fusion happening than it takes to get those reactions started. So of course, it takes a whole bunch of energy to power these lasers. We're going to go into that in detail in a little bit. And then we get the energy out from the thermonuclear fusion reactions. And a big thing that scientists are trying for at the NIF and at other fusion research facilities across the world, really, is to try to get out more energy than we put in to kick off that process. And we're not quite there yet. In the best shots at NIF, we have kind of a few percent of energy coming out in the thermonuclear fusion as we do in the laser energy that's driving the reactions. And that may not sound like a lot, but actually it is tremendous progress. And we're continuing to make progress every day and get bigger and bigger yield coming out, making more and more neutrons. We've been able to learn a lot and do a lot of really interesting science with all of the nuclear reactions that we are able to make. But it's true that we're also pushing harder every day because we really want to overcome that energy barrier. So why do we care about these facilities where we go through great effort to create fusion reactions? Well, as we mentioned, it's something that takes place when you're extremely hot and you're extremely dense. So this is a really interesting regime for physicists because we don't have access to materials that are under those conditions in just our everyday scenarios, right? Understanding what happens in a laboratory setting can help us understand hot, dense configurations in nature, say the sun. We actually learn things at the NIF about how the sun behaves and how materials behave under those conditions. Or we go to extreme pressures like you see at the core of Jupiter, and we can learn about the processes that are happening at the center of planets without having to go measure those planets themselves, but we can actually do it in a laboratory setting and measure it on this tiny scale. So another major application for NIF, which is really why the Department of Energy is spending taxpayer dollars to go through all this trouble, is that it helps us maintain and certify our nuclear weapons stockpile. So another place that we have very dense, very hot, and nuclear energy being created is inside of nuclear weapons. So the United States has stopped testing its nuclear weapons since the early 1990s. And that kicked off a tremendous challenge to be able to make progress on understanding the processes that are happening in them, as well as be able to make the important statements about its safety, its security, its reliability in the absence of doing any testing, even as these weapons are getting older and going through their lifetime. So the National Ignition Facility is really a cornerstone experimental facility where instead of creating those conditions by setting off a weapon buried underground in a desert somewhere, we can actually do it in a much safer, smaller, cleaner way inside of the National Ignition Facility, where we just have a millimeter pellet of hydrogen. We'll drive it with these lasers that you'll see in just a minute, and we can reach those conditions and understand the science of what's happening there in a much safer, controlled laboratory setting. Okay, so now that you have kind of some context for what we're trying to achieve and what's going on science-wise, I'd like to see if Lisa could pull up our first video for this evening. This is a video from 2009, back when the National Ignition Facility was first turning on, and it's a really great depiction of what it looks like inside and what happens when we fire the lasers. So Lisa, can you take that away for me?
The universe, for billions of years, has been lit by the fire of countless stars. In these stellar cauldrons, hydrogen nuclei are fused together to form helium nuclei, releasing energy that lights the heavens. Can we build the technology to harness this awesome energy on Earth? As we approach our planet, that is exactly what's happening today. Far beneath these clouds lies the National Ignition Facility, located at Lawrence Livermore National Laboratory in Livermore, California. This facility has been built to bring star power to Earth. It is the world's largest and highest energy laser system. Containing 192 laser beams, NIF will explore controlled nuclear fusion to ensure global security, enable sustainable clean energy, and advance our understanding of the universe. 85 feet tall, the laser and target area building is the size of 3 football fields. Inside are 2 parallel laser bays, each containing 96 beam lines. In this animation, which is millions of times slower than real time, we will follow the process for creating a miniature star in the target chamber by riding along with some of the laser beams. The process starts by first energizing the laser amplifiers in the 2 laser bays by dumping electrical energy stored in capacitors into flash lamps. They convert the energy to light that is absorbed by the laser glass in the amplifiers. Later, when the laser pulses pass through the glass, they will extract this energy, thereby increasing the laser beam energy. Our trip with the laser beams begins in the master oscillator room, where a very low energy laser pulse is created. This pulse is only 20 billionths of a second long in duration, which is a beam of light about 20 feet long. It's amplified and then split into 48 laser pulses, which are carried over to the 2 laser bays using fiber optic cables. Here, the 48 pulses are amplified in a preamplifier by a factor of about 10 billion. Then they're split into 192 pulses and sent into the main laser system. As we track 8 of these beams through the facility, you can see the path of the beams highlighted in red. The first amplification occurs in the power amplifier. It has 5 glass slabs that were energized by the powerful flash lamps. Then they travel to the main laser cavity that directs the laser light back and forth 4 times through 11 sets of laser amplifier glass in the main amplifier system. This gives the laser beams another boost of energy. During this time, optical components ensure that the beams maintain their required pulse shape, quality, and spatial uniformity. On the final pass through the optical system, the laser light is allowed to exit and travel back through the beam lines and up to the power amplifier once more to pick up even more energy before heading down the long stretch to the switch yard. In total, the energy of the laser beams is increased a quadrillion times as they travel more than 1,500 meters from the master oscillator room to the target chamber. In the switch yard, the parallel bundles of beams are rearranged into a conical configuration. That's so they can be focused into the center of the target chamber and onto the target assembly. The assembly holds the spherical fuel pellet containing hydrogen. Here you see the 8 beams split into 2 groups of 4 beams each, one group traveling up and the other traveling down, heading for equidistant entry ports on the target chamber. Finally, the beams pass through the final optics assemblies, which convert the original infrared laser light to ultraviolet. The beams then converge on the 10-millimeter target assembly called a hohlraum, generating a bath of X-rays. This causes the tiny target sphere to implode and ignite in a controlled, self-sustaining fusion reaction. The same process that powers the stars. This will be the start of a new journey that will bring not only discovery and innovation, but a lasting legacy to the future.
Great, thanks, Lisa. I always really like that synth music that they have going on, especially in the middle there. Really nice and heavy, gets me pumped up. This video really gives a sense for how awe-inspiring the scale of the National Ignition Facility is. You got to see how the laser beams get charged up over several football fields length of beam path, and then eventually get piped into this giant target chamber where they get focused on this 1 centimeter big gold cylinder, and inside of it there's a 1 millimeter large pellet of plastic or high density carbon filled with those hydrogen atoms where we're trying to get fusion reactions. So it's really impressive just on a scale. You can actually come visit the National Ignition Facility during normal times. I don't believe we're giving tours right now, but I encourage you to look out for them and sign up for one of the public tours when it reopens. It's really an exciting facility to see in person. To be a little more quantitative about some of the impressive scale of it, I'd like to talk about the power. I said it's the world's most energetic laser beams. It is very high powered laser. So when we fire all 192 laser beams and charge them up to their peak rated power, we deliver 500 terawatts of power to our targets. So what is a terawatt? Well, a watt is a unit of power corresponding to 1 joule, a unit of energy, per second. So remember that the light bulbs in your house might be something like 50 watts, right? Now, a kilowatt is 1,000 watts. Your microwave uses about a kilowatt of power while it's running. If you go another factor of 1,000, you go to a megawatt. That's 1 million watts. If you go another factor of 1,000, you get to gigawatt. So a large coal plant might be something like 500 megawatts or half a gigawatt. It's making a lot of power, right? After gigawatt comes terawatt, or 1 trillion watts. So if we have a 500 terawatt facility, that's something like 1 million coal plants going all at once, or about 1,000 times the average continuous production of the entire US electric grid. Now, wait a minute, you might say. The National Ignition Facility is inside the US, and so clearly we use electricity that we generate inside the US. Am I telling you that it's inside the US but uses 1,000 times more power than the entire country is usually producing? Yes. So the trick is to remember that power is energy divided by time. So imagine we were charging up our capacitor bank with just 1 watt of power. We do it for 1 second, so we put a joule in that capacitor. And then if we discharge it in 1 nanosecond, 1 billionth of a second, then we will already be to a gigawatt of power. So it's that very short time that makes us have so much power. And we have a fair bit of energy, but not a crazy amount. The NIF is about 2 megajoules, which is about enough to take 25 cups of coffee from room temperature and boil them. So not a freakish amount of energy overall, but because it's compressed into a few billionths of a second, it's a tremendous amount of power. So that's how that works out, and it's pretty impressive that we can deliver so much power on such a short time scale to these tiny little targets to very high precision. So next, I'd like to turn the page to supercomputers. Looks like I got a question about the NIF, so let me see if I can answer that. How long does it take for the tiny laser pulse until the laser reaches the target? So I don't know exactly offhand. I'm thinking a few microseconds, a few millionths of a second. So light travels about 1 foot per nanosecond, and looks like it has to go a couple thousand feet, so a couple thousand nanoseconds, a couple microseconds. It's certainly very, very fast, as we saw in that video, and that's my back of the envelope on the fly estimate. Hopefully I didn't butcher that too bad. Thanks for the question, Steve. I see we have another question about supercomputers, so I'll hold off to that until we talk about our supercomputers. So as you can see, it takes a lot of work to operate the National Ignition Facility. We fire about 1 experiment per day there. I think last year we had a little over 400, maybe close to 450 shots. That's people working around the clock, making sure everything is working properly. It takes a lot of work to make a shot happen. We have to wait for the optics to cool down so we don't damage them by firing the laser too fast. And we get to fire it about once a day. So this is an enormous facility, and we only get 1 shot a day. For every 1 experiment that we actually field, we will run hundreds, or in some cases, thousands of computer simulations so that we can predict what's going to happen, as well as so that we can analyze the data that comes out at the end after a shot. So it's in running these computational simulations to make the predictions and do the analysis that the supercomputers come in. So what does it mean to conduct a computer simulation of an experiment at the NIF? Well, what we do at Lawrence Livermore National Lab with our supercomputers is actually not all that different in character from what a Pixar or a Disney does when they make a computer animated film. You might be familiar with some films about sentient childhood toys, or fish trying to navigate their way home or something. So in order to make those films, it takes a whole team of people, right? There are certain software developers who write software to model how light bounces around. They might consider light coming from some light bulb and refracting through some glass. Maybe it goes through some water. Maybe it's scattering off of little sand that's in an aquarium tank or something. And then they're trying to calculate what it looks like, sort of, at a camera if you were to watch that. So there's the software developer people there. And then there are the digital artists who use that software, and they will define what's actually in the scene, right? They will say what color the light is. They will say what the shape of the aquarium is. They'll say how many fish are in it and what colors they are. They define all these properties, and then they will program a series of motions, and they will send it to some big computer clusters, not as big as ours, very proud of that, but certainly some very large computers to render images of what one might see under this scenario. So what we do with our supercomputers to model experiments is very analogous to that. We have the people that write the software, like me, who are computational physicists, and I will spend my day with pencil and paper, writing down mathematical equations for how light bounces around. Maybe instead of from a light bulb, it's from a laser. And I want to know how the gold of that cylinder wall absorbs the light and how it converts it into X-rays. And I will talk about how those X-rays get absorbed by our hydrogen capsule, and it blows off, and that gives this rocket effect, radially compressing the fuel inward. There's a lot of physics equations that go into that, the thermonuclear reactions, very importantly, that happen inside, and the energy that that gives off, and how that energy feeds back into the reactions happening inside our target there. So I will be writing down rules and coding up ways of solving those equations. I'll use C or C++ or Python, be coding them up, writing code most of the day. And then I kind of pass that framework, these multi-physics codes, over to the next team of people who we call designers. They design the experiments, and they're like our digital artists. They will take this tool and they will say, OK, well, if I have a laser energy that steps up in some certain way in time, and I shine it on a cylinder that's such and such big, and my capsule is made of a particular material, and here's how much light it absorbs, they kind of specify the initial conditions of the problem. And they'll say, OK, I want to run this for 10 nanoseconds. And they'll define sort of the time frame of their experiment. And then we take their problem definition together with my computer code, and the supercomputers will then take over and churn through the mathematics and those initial conditions and evolve in time dynamically our best guess at what nature is going to do. And at the end pops out from the computers a whole bunch of numbers kind of describing the state as a function of time. But we don't just look at the numbers usually. We usually have software that helps us visualize what it looks like. And we can use colors to represent densities of the fuels and whatnot. So what I would like to point out is that while people at animation studios have a goal of making things that are as entertaining and visually pleasing as possible, our goal is fairly different in that we want to make the most accurate, precise scientific predictions possible. And it's a tremendous challenge to be accurate when you're trying to model something that happens on just a few billionths of a second. So it's that extra requirement for being accurate that means we can't really take very many shortcuts. Certainly, we're always trying to figure out shortcuts we can take that don't lose the accuracy. But we really need the very, very powerful computers to have as much information and physics fidelity and accurate representation of nature as possible so that we can predict to, within a good margin, what's going to happen on these very tiny fraction of a second timescale energetic processes. So next, I'd like to show you one of these movies that we've made on the supercomputer. This movie is sort of a focused model of a little piece of the implosion of these targets at the NIF. It's actually not the whole process of lasers being absorbed by the gold canister and everything happening from there. We're actually starting with just a capsule, and we have a light fluid pushing on a heavy fluid. It's sort of like if you're trying to balance molasses on top of water. It's not stable, and they begin to build fingers and mix together. It's that same instability. It's called Rayleigh-Taylor instability. And I have an incredibly high resolution simulation of this process done on our flagship supercomputer. So before I talk about the specifications of the computer, I'd like you to see what type of movies we get out of it. So Lisa, if I could turn it back to you and watch our second video here. Lisa, do we have our video?
It's coming right up. Be right with you.
Perfect. Thanks for working on it. Wanted to make sure I didn't go silent there. I see a lot of great questions coming in from chat. This is exciting. I'll have to think about best way to answer these. OK, perfect. So our video is up. This movie was made by some colleagues of mine. It was actually made with one of the codes that I work on, so I'm very proud of this video. Here are some specifications, the details of which aren't too important. That first highlight is neat, 97.8 billion element simulation. So what that means is we have nearly 100 billion little computational pixels here. So we have a red fluid on the outside and a blue fluid on the inside. It's kind of peeled away so you can see what's happening on the inside and the outside. And we're compressing this sphere. That red fluid is squeezing in, and little ripples, due to this instability we talked about, mix into the blue fluid. And the white is where we can see the red and the blue mixing together. Now we're going to take a closer look so you can see just the really fine scale structures enabled by having 100 billion pixels in this simulation. We've now swapped the color scheme. We're going to zoom in. To me, this is just a beautiful animation. It looks sort of like you're stirring cream into your coffee in the morning. We get this turbulent fluid motion, and we're starting to mix together. And the fine scale structure that we see in this simulation is really helpful for us when we're running coarser simulations. We don't like to run. This took basically the whole Sierra Supercomputer for a couple days to run. And usually we run things on a smaller scale, maybe a few million pixels instead of 100 billion. And having these detailed high fidelity runs allows us to calibrate models for how fast things should be mixing in the event that we don't have so much resolution there. So thanks, Lisa. That was perfect. So that was a really beautiful video. And it was enabled, the reason we could have this 3D 100 billion zone simulation was because in fall of 2018, we got a brand new supercomputer at Lawrence Livermore. It's called the Sierra Supercomputer. And it's really interesting because it's powered by graphics processing units, GPUs. So when I come home after a long day of work and computational physics, I like to unwind by playing video games. I imagine some of you do too. In grad school, I played a lot of StarCraft 2. Nowadays, I'm playing some Apex Legends. And whenever you play video games at home, the images that you're seeing are being computed by a graphics card, a GPU, right? In your computer, you might have an NVIDIA such and such model. Well, what makes Sierra really interesting is that it's also powered by GPUs. But instead of, say, your computer at home that has one GPU, the Sierra Supercomputer has 17,280 NVIDIA graphics cards. And the neat thing is that they can all work together to work on the same problem at the same time. It is a huge challenge for the computer scientists, the computational physicists, and the computer hardware people to make sure that all those graphics cards can communicate with each other very efficiently, and that we can put those cards to good use. So the movie I showed you just now used just over 16,000 of these GPUs together. Another piece of this is these aren't just bargain basement GPUs that they were getting ready to throw away at Best Buy and we hooked them up together. These are actually state-of-the-art, bleeding edge, very high performance GPUs. So my NVIDIA GPU at home is about 6 gigabytes of memory. Each one of the 17,000 inside of Sierra is 16 gigabytes. So it is incredibly powerful. It's not the kind of thing you'd use to play video games on. It's really for these high performance computing applications. So when we flipped the Sierra Supercomputer on in the fall of 2018, there was a couple months of working out the kinks and running test cases to see how fast it was. And at the time, after a couple months of troubleshooting, we were able to reach very high level performance, and it clocked in at #2 fastest in the world. The #1 fastest at the time was a sister computer at Oak Ridge National Lab called Summit. And actually, the two computers have the same hardware inside of them. It's just that Summit has about 50% more GPUs, 27,648 to be exact, last I was informed. And because we teamed up together, we were able to pool our development resources. I believe the DOE spent something like $350 million for the two computers together. So very expensive machines. But then Livermore and Oak Ridge both got these world-class powerhouse computers. So the way we measure computer speed is with flops, floating point operations per second. It's a measure of how many simple like addition, multiplication things you can do together. And your computer at home might have something like a 2 gigahertz processor, or it does 2 billion floating point operations per second. The Sierra supercomputer is 125 petaflops, which is about 50 million times more calculations than a single 2 gigahertz laptop. So it's like 50 million laptops working together at the same time on the same problem. So as we look forward, you might wonder, well, okay, we want Sierra to be even faster. Can we just keep adding GPUs? Why not go up to 100,000 or 1,000,000 eventually? Well, one really interesting piece about supercomputing is that the main limiting factor is really how much power these computers consume. So when you're at home and you're playing games, your computer uses a lot of power, and then it generates a lot of heat, and you have to cool it with your fans. Well, Livermore has these incredibly huge air conditioner units and water coolers that are used to cool down the supercomputers. So to run Sierra, and it's usually running around the clock, it takes 11 megawatts of electricity to keep it cool. Now, that's a lot of electricity. A typical household on average uses 1 kilowatt of electricity continuously if you average throughout the day. So the electricity to run Sierra Supercomputer is something like 10,000 homes worth of electricity. It's really a lot. And unlike the NIF, where we had big power, but for tiny little times, so it's not that much electricity that it's using over the day, the Sierra Supercomputer is on a lot, and it costs a good bit of money to pay for that electricity, as well as all the infrastructure that can keep the computer cool. So it's an incredibly impressive device. And for a couple decades, the generations of computers have been stuck at about 10 megawatts. And it's really advances in more efficient computing hardware that allows us to get these new generations of machines in these big performance loops. Okay, so I showed you a movie that was studying processes that happen at the National Ignition Facility with Sierra Supercomputer. There's a lot of different people who run a lot of different codes on these supercomputers. One big application, these computers are funded by the National Nuclear Security Administration and cohesive with the stockpile stewardship mission of the National Ignition Facility. We use these supercomputers to run simulations of the nuclear stockpile. Instead of performing an experiment where we would set off a nuclear weapon and measure what happens, we have this sort of virtual test ground where we can do things entirely in digital space and study what's happening, learn physics, make sure that we have safety, security, and reliability of the stockpile without having to resort to actual testing. So that's an extremely important application that motivates the procurement of these massive machines. They also get used for a lot of different things. They get used for climate modeling calculations. It's really tremendously difficult problem to model forward the energy balance of the planet and all the different forcing mechanisms. We really need the best computers possible to make the highest fidelity predictions of those processes so that we can make smart policy decisions. There's also some really interesting medical applications. We've been working on the cancer moonshot, and physicists are working with biologists to model different pathways and mechanisms underlying certain types of cancers. And we hope to understand the mechanisms better by being able to model them well on the computer, and then we can come up with better treatments and ways to fight it. Now that everybody is at home and we are spending a tremendous amount of money as a nation to fight the COVID pandemic, as well as losing the economic costs of people not being able to work at their full capacity, we are using our supercomputers and the technical expertise at Livermore to be able to model potential drug interactions. Instead of going out and having to test 1,000 different drugs, I don't know how many they're thinking about, but a large number, we can sort of narrow down to a small list of the ones that we think are most promising and really speed up that time of being able to get good treatments out. So that's another really exciting application that's come on recently. So as I mentioned at the beginning, we just got bumped down this week from the #2 supercomputer to the #3 in the world. Japan unveiled a new machine called Fugaku, which is 400 petaflops, about 3 times faster than Sierra. It's powered not by GPUs, interestingly, but by these ARM processors. They're these reduced instruction processors that have been popular for cell phones and mobile devices. If we talk about that lower power aspect of computing, then maybe not too much of a surprise that we're seeing that, but that's really interesting. But don't you worry, Livermore has some ambitions for what the next generation is going to be. One of the great things about working with supercomputers is it's always evolving technology, and even before we're done getting used to the current one, we're already planning the next one. So I'll kick this to Lisa for one final video that I have, and then we'll wrap up and address your questions. And this one will take a forward-looking perspective towards a new machine we're going to get in a couple of years. So go ahead and take that away when you're ready, Lisa.
What supercomputers are here in this video, and they are indeed super. The fastest machines today are in the realm of petascale computing. That's more than a quadrillion computing operations per second. The most powerful computer in the world today is Summit, the supercomputer at Oak Ridge National Lab. It's followed closely by Lawrence Livermore's Sierra Supercomputer. But even today's most powerful high-performance machines can't keep up with the demands of the increasingly complex simulations required for national security, precision medicine, climate research, and a host of other areas of basic science. So, what's next? Some computing experts have called improving computing performance on this huge scale the space race of this century. Because after petascale computing comes exascale computing. If petascale is a quadrillion calculations per second, exascale is a quintillion operations per second. That's 18 zeros in 1 second, 10 to the 18th. And by the way, that's why Exascale Day is on October 18th. Get it? It's a small word for an almost unimaginably big number. If we went back in time a quintillion seconds, that's about 32 billion years ago, 18 billion years before the Big Bang. A quintillion is about the number of neurons in 10 million human brains. And if you somehow linked the top 100 fastest and most powerful supercomputers in the world right now and had them all work together on a single problem, you still wouldn't reach the computing power of one exascale system. If we look back at the progress we've made in improving computing power, we've made these strides because we've been able to pack more and more computing power into smaller and smaller spaces. That improvement in power has been holding steady for many years, but we're starting to see it slow down. We can't get the transistors any smaller. And plus, moving data around within a computing system that large takes so much energy. Huge leaps in computing also require leaps in the accompanying infrastructure. Interdisciplinary innovation has resulted in improvements to the architecture, data storage and management, and the kinds of software that can run on these machines. This and much more is what has made exascale computing a reality. The nation's first exascale system, Aurora, is slated for arrival at Argonne National Lab in 2021, followed later that year by Frontier at Oak Ridge National Lab and El Capitan at Lawrence Livermore in 2022, projected to perform at more than 1.5 exaflops. That's 1.5 quintillion operations per second. But why do we need this huge leap in computing power? At a national lab like Lawrence Livermore, scientists rely on computer modeling and simulations to solve problems that are way beyond the scope of any human. And see, the universe is in 3D, and the ability to incorporate additional physics into 3D simulations and perform them regularly means that the information scientists get from these models will be closer than ever before to what happens in the real world. El Capitan will allow scientists and physicists to perform larger and higher resolution 3D simulations than ever before, and fast. Simulations that might take a week to perform on Sierra, Livermore's existing petascale computer, could be completed in a single workday on El Capitan. El Capitan's primary mission will be supporting America's national security missions, ensuring the safety, security, and effectiveness of the nation's nuclear stockpile in the absence of underground testing. Across the Department of Energy, exascale computing will help scientists answer some of the biggest and most fundamental questions humanity has. It will allow for faster, more detailed models in areas of basic science, such as predicting the effects of climate change, simulating how drug molecules interact with the body in order to create more effective medications, optimizing designs for 3D printing, studying earthquakes, or how the 100 billion neurons in the human brain connect and function. Throughout history, we've pushed the boundaries of humanity's ability to understand and ask questions of our universe. And exascale computing is simply the next step in better, faster science. And what's next? Beyond exascale computing, beyond the boundary of Moore's law, into the realm of fields like quantum computing, well, we can only imagine.
Awesome. That's great. I always enjoy that video. So I hope that you enjoyed our discussion today, learning a bit about the National Ignition Facility and supercomputing at Livermore, whether it's our current machine, Sierra, or El Capitan that we're looking towards receiving in just a couple of years. As we wrap things up and head towards some questions, I see some great questions coming in. Please keep them coming. I'd like to step back and reflect briefly on what's at the core of my role as a computational physicist and why I find it so enjoyable. And I want to share an analogy that one of my favorite physicists, Richard Feynman, made. And he said that the endeavor of physics is about writing down laws for how nature is behaving. And doing that is sort of like you're watching some giant cosmic game of chess. Maybe you only get to see a small corner of the chessboard. Maybe you only get to take glimpses at it at certain times. And this chessboard is tremendously complicated. There's so many things going on at once. You can't possibly understand all the things that are happening. But as you watch and take careful measurements, you begin to recognize patterns. Maybe a bishop can only move diagonally. And it's recognizing those patterns and turning them into rules that you write down that is really the process of physics and our effort of understanding the laws governing how nature behaves. For me, as a computational physicist, I think supercomputing is really the ultimate embodiment of that process, because we get to take those laws and we get to solve them with the best methods we know how on the fastest computers in the world and make predictions. And those predictions are incredibly precise, but also we're always getting surprised that nature's chessboard is behaving a little bit differently than we expected. And I'm constantly refining my own understanding. I get to understand them better to try to be so systematic that I can solve them on computers and make predictions about what's really going to happen. As well as a scientific community, we're learning things. We're learning better ways to do it, approximations we can make that are insightful and tell us what's happening and make the computer's jobs easier, as well as sometimes processes that we didn't know were important, but then we decide are important to include. So thank you so much for your attention, and please do keep the questions coming. Before I forget, I certainly very much want to thank the Chabot Space and Science Center again for having me. It's been really tremendous. And if you're interested in more, I would encourage you to subscribe to Livermore's YouTube channel. And there's some great series. The last one we just watched was from the Inside the Lab series. There's a new video recently about our efforts with supercomputing with COVID. I think all of those are really interesting. For my content, there's a series of videos called Learning with Leland. You can watch swim caps getting dropped on my head and me try to feed donuts to my car to make it run. So there's some fun things there. So thank you so much for your attention. And let me go and answer some of the great questions that I see coming in. So we have a couple of them about NIF, and then we can take some supercomputing ones. I see one from Tom. What are the variables that you manipulate during experiments at the NIF? So there's a lot of different things that you can imagine riffing on in that general cartoon that you saw, this gold cylinder with the capsule in the middle. So the materials that we use for that capsule are very important. The size of the capsule is also very important. The laser profile is a really interesting piece of the physics. So we have tremendous precision with how much energy we can deliver as a function of time. And people will do things where they try to squeeze it a bit first and then hit it harder. There's a lot of games that people play with the pointing of the beams inside that gold cylinder. We start with more energy outside and then put more on the inside to try to control the shape. We actually have a lot of interesting parameters we can do there. People are brainstorming about interesting shapes to the hull realm. There's a lot of things you can think about tweaking to try and optimize what you get in an individual experiment. And actually, there's a really wide range of experiments that we do at the NIF. So I hope that gives you a flavor of what types of things we do there. Another question I see come up from Jeanette. Was there an experiment that gave you results completely unexpected? So it depends on what you mean by completely. I would say that in every experiment, we find interesting things that we didn't expect ahead of time. We run what we call pre-shot simulations of what we think is going to happen. And then inevitably, there's always these post-shot simulations where we try and understand, well, what was different from what we thought? And maybe it's something simple like there was more gas inside the capsule than we thought before. Or maybe the laser, we measured how it behaved, and it was a little bit different than what we asked for. So then we go and model and see those implications. But there are also some major things. I mean, you look at, we had our national ignition campaign very early on. And it's fair to say that the simulation results we did before that, we were expecting to get more fusion reactions out than we ended up getting experimentally. And it was a huge scientific effort to really understand why. And over time, we've come to do a much better job of modeling these things. We found it often wasn't something fundamentally wrong with our computer codes. It wasn't some totally missing equation or something. But as we went to 3D and incorporated all of the little features that we could, there's these little tubes that they use to fill it with gas. There's these little tents that hold it. And as you incorporate those features that originally you might think, well, it's kind of a pain and maybe it's not important because it's a really small little tent. As you include those, we've actually gotten more and more accurate, and the discrepancies from the simulations and the experiment go away, and we find really nice agreement. So certainly there's been a lot of exciting surprises, and we've learned an awful lot, both with just the experiments that we planned and got new data out that we were interested in, as well as better ways to use our computational tools. OK, let's see. What other questions do we have? Right, some questions from Jacob. Are supercomputers getting physically larger in size as we just tack on more products to make this happen, or are there other dominant factors at play? It really is the shrinking of the processor units, the hardware. I don't think the computers themselves are really getting that much bigger. You can walk through the computing facility, which is really wicked cool, by the way. And the computers themselves are about similar size. We have our advanced machines that are the flagship ones, and sometimes those will be a bit bigger, but it's really the shrinking of the hardware that allows us to get more done on those facilities. What, if anything, have you learned, this is from Heather, from the international fusion experiment and private efforts that have led to improvements in the NIF? So lots of great things in that question. So in my own career, I've actually worked on a couple different kinds of fusion. I started in a lab at University of Colorado on something called a field reverse configuration. It was some magnetic fields in a specific donut-like geometry. And that was a university scale, fairly small project, really got me excited about plasma physics and fusion energy. Then I went to Princeton, and there we have a pretty large magnetic device called the tokamak. You get to hear all the time about some interesting, innovative things. There are companies that are trying some really outside the box ideas. And certainly on a just general fusion quest, I think it's healthy to be trying various different ideas. And if we can inspire investment from the private industry in addition to the investments that the government is making, I think that's a wonderful thing, as long as the investors have realistic expectations of the probability of any one idea working out and becoming a breakthrough power plant method. In terms of the National Ignition Facility and our laser-driven high energy density, we're kind of focusing on a different application than the power systems. Certainly, we do have a lot of collaborations with university partners. People have played a lot of work in the optics and making things work. I'm not familiar with too many like private inertial confinement, this kind of non-magnetic brand of fusion things, though I think I heard about one in the UK recently that was novel. So I hope that gives you a sense. Maybe I'll take one more question, and then I'll kick it back to Lisa so we don't go too far over time. what's the biggest hurdle to scientists making effective use of supercomputers today? That's a question from Lee, another Lee out there. That's awesome. So that's a great question. It really is a huge effort to make use of the ever-changing architectures that we're getting. So we've devoted a lot of time and energy into adapting from our typical general purpose processors, our CPUs, to getting these big codes to work on the GPUs. It's just, you have to structure them very differently. And I think historically it's very interesting because the early days of supercomputing were really inspired by the government big lab efforts. In fact, back in 1953, Livermore's first big procurement was to buy a computer. It has a long history of computing. And so during those early days, the computer manufacturers were catering to the scientists' needs, right? We were the ones driving the problem, and certainly those computers were very difficult to use, but they were motivated by adapting to our applications. Now, in recent time, it's really interesting that those trends have sort of switched. We talk about 17,000 GPUs that are inside Sierra, and between us and Oak Ridge, we spent $350 million over a couple years to get these really big machines. And certainly that's not nothing to a company like NVIDIA, but they sell a lot of graphics cards, right? They sell millions, and our 17,000 is just not that many. So they didn't set out to make graphics cards for us. They set out to make them out for, well, graphics, right? And I think it's a really exciting scientific challenge to get to adapt the codes to use this hardware. And we have to really think sometimes very carefully about how to sort of restructure our algorithms, how to reorganize things. For instance, for the GPUs, it can be a big efficiency loss to shift the data around. You have your CPUs and they have some RAM. And sometimes you need to do some things there, but then you want to shift off a chunk of work to the GPUs. And usually when we adapt our codes to this new generation of hardware, they're actually slower the first time we run them than they were on the old computers. But we go and say, hey, where are we shifting around data where we don't have to be? And we start optimizing it and go through this process. And then eventually we compare the performance and we're coming out ahead of the old hardware. So it's really fascinating to try to adapt to those different constraints that are being driven by industry. And I think it's really cool that early government investment and things like big computers can transform into something that impacts people everyday lives and they get to use them in their home. So with that, let me wrap up. Thank you for the questions. I'm so sorry for the ones that I didn't get to. A lot of great questions came out, and I will thank the Chabot Space and Science Center one more time and kick it back to Lisa.
Wow, thank you, Lee. That was amazing. My mind is just exploding with quantum leap, in fact.
Thank you. I'm so glad.
And I just want to thank all of our guests who joined us from near and far this evening. And don't forget to tune in every Friday for a variety of engaging programs that you can enjoy right from the comfort of home. Our next event will be Friday, July 3rd for our big moon mashup. You don't want to miss it. Visit our website, chabotspace.org, and click on the events button to see a complete listing of our virtual programs, including our live telescope viewing. That right back there.
Awesome.
Now more than ever, as we wrap up, as our time has come to an end, please consider your support of Chabot Space and Science Center and our vital role in the community with STEM education. You can donate via our website, chabotspace.org, and click on the donate button, or become a member or get involved. Once we're back up and running, become a volunteer. There's lots of ways to get involved. I hope you're staying safe and well. Good night, and we'll see you next time.